Okay, we'll start with the airfoil geometry. So you are familiar with the airfoil, right? Symmetrical airfoil and symmetrical airfoil. Am I audible?
Yes, sir.
Yes, sir.
Okay. 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 So this is the leading edge. That is, this forwardmost point is the leading edge, and this point is the trailing edge of the airfoil. And the straight line that joins this leading edge and trailing edge is the chord line. Okay. So the straight line which joins the leading edge and the trailing edge of the airfoil is called chord line. Then we have additionally camber line. So this is the camber line. So this camber line equally divides the airfoil. Okay. So the difference between the chord line and camber line. So chord line is just a straight line which joins the leading edge and trailing edge, but camber line equally divides the airfoil, and distance between this camber line and chord line is the camber. Okay, the blue color line is the mean camber line, and the distance between camber line and this chord line is the camber. Is it clear? And this is the upper surface, this is the lower surface, and distance between these two things is called thickness, and here they mention the maximum thickness. Okay, thickness can be measured anywhere, but here they show the maximum thickness, and both this maximum thickness and this camber should be measured perpendicular to the chord line. That is very important. Okay, both this camber and this maximum thickness should be measured perpendicular to the chord line. Is that clear? The dimensions of the airfoil: leading edge point, trailing edge point, chord line, camber line. Distance between camber line and chord line is the camber, this distance, and this is the thickness, distance between upper surface and lower surface profile. And in the front, you can fit one circle. Okay, so leading edge circle, and the circle radius will be usually 0.2 C. What does that mean, 0.2 C? Any idea?
So 20% of chord line.
Yeah, good. So chord we used to mention as C. So 0.2 C means it is around 20% of the chord. Okay. And why most of the subsonic airfoils are in the circular shape? Why it can be this sharp one? Why it is not like that? Why it is blunt in the leading edge? Compared to that, this is very smooth, right? This is a streamline pattern, right? Why we are going for this circular pattern?
So maybe due to stresses, because on subsonic speeds, if it is like totally sharp in the front, then there might be stresses on the airfoil as compared to the blunt one, or maybe the normal airfoils.
Okay. In terms of stress, you are telling?
Yes, sir.
Okay. And
to accelerate the flows.
okay, for better acceleration. Okay, good. And I think last lab I explained the Konda effect, right? What is the Konda effect I explained? So when the flow passes through the curved surfaces and this experiences the maximum flow deflection, so it will be accelerated to the maximum velocity. Okay, if there is a flow pass through the curved surfaces, so you can see the flow deflection, it is maximum, so it experiences the better acceleration, so velocity increases, pressure decreases. Okay, so because of this curved surface, we are having the low pressure in the front, and here we have the atmospheric pressure, so that creates little bit a forward force. Normally there will be a drag force which is very high, and because of this shape, there is a small opposite component, okay, so that the drag is little bit reduced. Okay, so as you said, it is for better acceleration, so that we are getting the low pressure region in the front, and this effect is called Konda effect. And this sharp edge, we will use it only for the supersonic flows, just to reduce the shock wave. If you use this rounded leading edge in the supersonic flow, there will be a strong bow shock. So this will unnecessarily increase the wave drag. But here, if you use this type of sharp leading edge airfoil in the supersonic, there will be a weak oblique shock. So this produces minimum wave drag. So for that purpose, for supersonic airfoils, we will use the sharp leading edge. Okay, but for subsonic, for the better acceleration and to have the effect of this benefit of Konda effect, we have these circular cross sections in the front. Okay, then NACA series, this have you heard? NACA airfoils.
Yes, sir.
What is the abbreviation of NACA?
Sir, using it somewhere we can like plot any type of airfoil.
No, what is this? NACA indicates?
National Aeronautics.
National Aeronautics. This AC. National Advisory Committee for Aeronautics. Okay. So here they found n number of airfoils. Okay. So initially they found 4 series. This is a 4 series airfoil. Then they further improved that to the 5 series airfoil. Then they further modified into 6 series. Actually, they have a NACA series of 1, 4, 5, 6, 7, 8 like that. Then supercritical like that. N number of airfoils they have. Okay, and in the commercial aircraft, mostly will use this NACA 4 series, 5 series, 6 series airfoil. This is the one example of NACA 4 series. It can be of any number. So 2412, 4412, or maybe 6218. Okay, so these are all the different examples of 4 series airfoil. I have taken only one model. This is most used model, NACA 2412. And each number indicates the geometry of the airfoil. Okay, so always in all the airfoil, last 2 digit indicates the maximum thickness of the airfoil. Okay, whether it is 4 series, 5 series, 6 series, last 2 digit indicates the maximum thickness. Assume the total chord of the airfoil is 100 mm, then this 12, the rating is 12 divided by 100 into C, that means 12 mm. Okay, so the maximum thickness of this airfoil is 12 mm. If it is given as 16, then it is 16 mm. Okay, 16% of the chord. So always for all the airfoil, the last digit is the maximum thickness. Actually, this multiplication etc. and all you have to memorize in the exam. In the 4 marks, 3 marks and all, they may ask what is the nomenclature of NACA 4 series airfoil. You have to write first digit divided by 100 into C gives maximum camber. This you have to memorize because this is the definition. Okay. So last digit is maximum thickness, and in the 4 series, first digit is the maximum thickness. So 2 divided by the first term divided by 100 into C gives the maximum thickness. So here we are getting 2 mm. So sorry, maximum camber. You know what is meant by camber. So this is mean camber line. This is this. Assume this is the chord line, and the distance between those two is the camber. So here they mention maximum camber is 2 mm. Okay. Then the next digit, this 4 divided by 100 into C shows the location of maximum camber. So here we are getting 40 mm. That means from the leading edge, this maximum camber is located at 40 mm. That is 40% of the camber. Then maximum thickness is 12 mm. Like that, from these numbers, we can get the geometrical parameter of the NACA 4 series airfoil. Is it clear? So first digit shows the maximum camber. Second digit shows the location of that maximum camber. Last two digits shows the maximum thickness. Is that clear? And this,
Yes, sir.
this multiplication you have to memorize, okay? Because it is not constant for all the airfoils, it will vary, so you have to memorize. Then if you take NACA 5 series, so first digit shows the CL design, that is first term 2 into 3 by 2 divided by 10 shows the CL design. I will explain what is this of lift. Okay, then the second two digits multiply 1 by 2 divided by 100 into C gives the location of maximum camber. Then again last two digit is the maximum thickness. So if you compare 4 and 5 series, so last two digit is the maximum thickness, and before that we have the location of maximum camber. Only this varies. Here it is maximum camber, here it is CL design. Only that is varies. And again here we found the location of maximum camber is 15 mm. Previously for this 4 series, it is at 40 mm. And both are the same thickness, 12 mm thickness. And this CL design that I will explain. Actually, if you, for example, if you take this airfoil, assume this is 0 degree, this may be the 90 degree, this may be the 10 degree, 20 degree, 20 degree, 30 degree angle of attacks, like that. So for every angle of attack, we will get different CL value, right? If the angle of attack is increased, CL also will increase, CD also will increase. And this CL means whenever the flow is tangent to this leading edge of the camber line, here you can easily mention. So whenever the flow is tangent to the leading edge of this camber line, then the corresponding CL is called CL design. Is that clear? For different flow velocity, flow angle of attack, we will get different CL. If angle of attack increases, CL also will increase. Okay, so CL design means the flow has to be tangent to the leading edge of this camber line. That time you will get on CL, that is called CL design. Do you understand? Now should I repeat? Hello, am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So this is 5 series. Then 6 series, here we have the 5 digits. Okay, don't think 4 series means only 4 digit will be there. 5 series means 5 digit. 6 series means 6 digit. It is not like that. Okay, so 6 series also we have only 5 digits. And again, last 2 digit is the maximum thickness. And first digit, it simply shows the series name. Okay, it doesn't have any meaning. So simply it shows this series name, because if you don't include this 6, it will be like 6212. Then it will be similar to the 4 series airfoil. You will get confused. So to differentiate the 4 series and 6 series, they added another one 6 in front of it. Okay, so we may have 62412. Okay, if the 6 is not added, then it is like the 4 series airfoil. So to differentiate, they added the 6 in front. So first digit simply shows the series name, and next digit divided by 100 into C shows the location of minimum pressure. The next digit shows the CL design. Then last 2 digits shows the maximum thickness. And this location of minimum pressure means if the flow is accelerated to the maximum, then at that point only we will get the minimum pressure, right? So it is approximately equal to the maximum camber. Okay, so here we can say the maximum camber location is around 60 mm, around 60% of the chord. That's it. But these are all the definitions. No other way you have to memorize. Okay, this multiplication factor, etc. and all you have to memorize. This terms also varies for every airfoils. Only the last term is constant, maximum thickness is constant. All other terms will vary. So this you have to memorize. Okay, now we will see what is the need of 4 series, 5 series, 6 series. Okay. So initially they tested the 4 series. They kept this maximum camber at the 40%, 50%, etc. and all. From that they found, so this increases the CL, CD also, but so okay, this is the first one, this you leave it. So actually for the 4 series, we have the theoretical formula. Then from that they understand how each parameter affects the flow property. Then they went for the experimentation. Based on that, they created the 5 series. So in the 5 series, what they did, they moved the maximum camber location to the forward direction. So because of that, what will happen? We are getting more curvature here. So if the curvature is increasing, acceleration also will increase, then CL also will increase. But whenever CL increases, CD also it will increase. Okay. So compared to the 4 series, in the 5 series, they moved the maximum camber location to the forward direction so that the curvature is increased, acceleration, CL, everything is increased. But this increases the CD also because the flow is attached only up to this, then there will be a separation. So CD also increased. Then further they went for the 6th series. Here they moved the minimum pressure or maximum acceleration point towards the middle, even after the middle, that is 60%, for example. So here what happens, the flow is accelerated and attached up to this point. Okay, after that only it is separates. So the main aim of the 6th series is to maintain the attached flow, laminar flow. Okay, so sometimes we are calling this as the laminar airfoil also. So you can see 4 series, 5 series, this is the drag curve, it is little bit higher, and for the 6th series it is further reduced. Okay, so compared to the 4 and 5 series, for certain angle 6 series produces very less drag. So nowadays mostly we will use this type of 6 series airfoils only in the commercial aircraft. There is laminar flow airfoils. Is that clear? How the profile varied and these definitions?
Yes, sir.
Okay. And here I explained the flow over the airfoil. So here I explained the mainly flow separation. What will happen? Assume there is a flow over the airfoil. In the real condition, there will be a viscous effect, there will be a compressible effect, everything will be there, right? So because of the viscous, there will be a friction between the airflow and this wall. Okay. So due to the friction, the kinetic energy of the flow will reduce. That is, maybe velocity will reduce. Okay. So that at some point it will completely lose its kinetic energy, that is velocity will be zero. From that point onwards the flow will separate. Okay, so due to the viscous effect, it is due to the friction between wall and the flow, the kinetic energy of the flow is decreasing along this chord line. At some point the flow will lose its complete momentum, so from that point onwards it will separate. So this is called separation point. So because of the separation we are getting the large wake region. Okay, so here the flow hits the leading edge, so we have high pressure region, and behind that there is a wake, there is no flow at all, so we have the low pressure region. So because of this pressure difference, so here high pressure, here low pressure, we are getting the force in this direction. Always force will be from high pressure to low pressure. That force is called drag force. Is that clear?
Yes.
Okay. We can say this is the pressure drag or form drag. Okay. Pressure drag or form drag, both are equal. Two different names. And this flow separation, this wake region drag cannot be avoided. It will be there in the physical flow. The only possibility is we can delay the flow separation. If you are reading many research journals and all, you may come to the term like delaying the flow separation. So delaying means we are moving this separation point rearward. Instead of from here to here, if you move it, then the flow will be attached up to this point. Then from here only it will separate. Now you see only this much wake we have. Okay, so the wake is reduced. If you move the separation point rearward, then the pressure difference also reduced, drag also can be reduced. Only this is possible in the real condition. Okay, so complete removal of separation, wake and all not possible. The only possibility is moving the separation point rearward. That is called delaying the separation. Okay, and to do this delaying the separation, we have different flow control methods. So passive flow control method, active flow control methods. These things we'll start discussing in the 5th unit. So in the passive, so we may place the vortex generator here. Have you seen this vortex generator? Like small fin attached on the airfoil or wing?
Yes, sir.
Okay, so this is one type of passive vortex active flow control method. So what will happen if you place this fin-like shape? So the flow will move over it, and behind that there is a vacuum, right? There is no flow, right? So the flow will try to curl so that it creates the axial vortices. Okay, so vortices means in the center it will have the low pressure. Okay, the vortices will have low pressure in the center. So this shape is mainly to produce the axial vortex. That means low pressure region, and this low pressure region sucks the separated flow. For example, if the flow separates from here, okay, there if you are placing this vortex generator, it will create the axial vortex. That means low pressure region that sucks the separated flow so that it will be attached up to further distance. This what is it? The detailed discussion we will do it in the 5th unit. So this is about flow separation, separation point, wake, pressure, drag and all. Is that clear? Separation and separation point?
Yes, sir.
Yes, sir.
Okay. And if you increase the angle, then we will get the large wake. This is small angle of attack, and the separation point is here. Okay, so we are getting this much wake thickness, and if you increase the angle, then separation point move depends upon the increase in angle. Now here it is, this is the separation point. We are getting the large wake. If we further increase the angle, then the flow will separate from this leading edge itself. There is no flow attached over the airfoil. That is called stall. That is complete loss of lift. Okay, at least these stages there will be a lift and drag, but once it is separate from this leading edge itself, so it will not produce any stall, any lift. It will produce only drag. So that condition is called stall. So in this GIF file you can see. So initially the separation point is here, and it is moving here like that. Okay, and here also in this video, initially it is here, then it is moving here. Now see, it is separating from the leading edge itself. You can pause this, right? Or cannot pause. Okay, so if it is completely separating from the leading edge, that is called stall. That is loss of lift. These things are all just additional informations. So as the angle of attack increases, separation point will move forward. So wake region will increase, drag also will increase. And this is CL/CD curve of the airfoil. As the angle increases, CL will increase. Okay, CD also will increase, and everything will happen up to the stalling angle. After the stall, there is a loss of lift, and drag will go like this. Okay, up to that, there you can see one curve, and after the stalling, it will go to the maximum. And here I explained two different airfoils: symmetrical airfoil, unsymmetrical airfoil. And if you place that symmetrical airfoil at 0 degree angle of attack, so about this line, the profile is symmetrical, then the pressure distribution also symmetrical. So there is no net pressure difference along this direction. So lift is 0. Okay, so the profile is symmetry along this chord line, along this axis. Then pressure distribution also will be flow, there is streamline pattern, pressure distribution, everything will be symmetrical. Then lift is 0. That's why at 0 degree angle of attack, CL is 0 for symmetrical airfoil. But if you take the cambered airfoil, even at 0 degree angle of attack, because of this curved surface, there will be a flow acceleration on the upper surface and deceleration on the lower surface. Because of that, there is a net pressure difference and there will be a lift. Okay, so 0 degree angle of attack, there will be a finite lift. for the cambered airfoil. And this cambered airfoil will produce zero lift only at some negative angles. Okay. And both airfoils stall at a particular angle. Up to that, the flow will be attached. After that, the flow will be detached from the leading edge itself. So this is a stall. So this is called complete loss of lift. And the stalling angle, mostly it will be from 12 degree to 60 degree. It will vary for different airfoils. Is that clear?
Yes.
Yes, sir.
Okay.
Yes, sir.
Okay. Actually, all these things you will study in the elements of aeronautics, but I think they removed from your batch or from the previous batch. So I'm just briefing these things also now. And this is the mission profile. So mission profile means from starting to ending of the flight duration, this shows the different level of the aircraft. Okay, so initially there will be a ground run, then it will take off, then it will climb, then there will be a cruising, that is steady level flight, then it will descend and land, again there will be a ground run. Okay, so the different level of aircraft in a single flight, the graph is presenting. So that is called mission profile. And you know, during the climb and takeoff and climb, the velocity will be very less. Okay, so you know the lift formula, right? Of rho v squared s cl. So density, velocity, area of the wing, and lift coefficient. This is lift. Okay. So during the takeoff and climb, that time only the flight is just starting. So the velocity will be less, but we need sufficient lift to keep that aircraft in the air. So in that case, what we are doing, so this is reduced. So we are increasing this CL. Okay, so that we can produce the enough lift. And to increase the CL, we are maintaining the high angle of attack, right? So as the angle increases, here we see, as the angle increases, CL also increases, then the total lift is increasing, so that we can keep this aircraft in the air. Is that clear? But if CL
Yes, sir.
increases, CD also will increase. So most of the flow control methods, even passive control, active control and all, is applicable to this climbing and takeoff conditions. Okay, here only there will be a large separation. To reduce the separation only, all that flow control methods are used. Okay, this is for the takeoff and climb. But if you take the cruise, aircraft will be in the steady level condition. What is it, steady level flight? Have you heard this term, steady level flight? How the forces will be?
Yes, sir.
Okay, so in the steady level flight, all the forces are equal. That is, lift will be equal to the weight, thrust will be equal to the drag. Okay, so in the cruising, aircraft will be in the steady level condition, but here the speed will be very high. Okay, so in the cruising condition, speed is very high, so the smaller lift CL is sufficient, so it is kept at the small angle. Mostly in the cruising condition, if you check the angle of attack for the commercial aircraft, it will be between 3 to 5 degree or maximum 6 degree. Okay, but here if you see, it will be maximum 14 degree, 16 degree, depends upon the airfoil, it will vary during the takeoff. But in the cruise, velocity is very high, so the smaller lift is, so smaller CL is sufficient. So if CL decreases, CD also will decrease, and so that we can save a lot of fuel during these cruising conditions. And in the complete mission profile, if you take this cruising, this takes approximately 60% to 80% of the total mission. Okay, so minimum 60%, maximum 80% it takes. So in this cruising phase, we are maintaining the very low drag so that we can save the fuel. Is that clear, mission profile? So here velocity is less, so we are increasing the angle and increasing the CL so that enough lift is produced. Here velocity is very high, so the smaller angle is sufficient to produce the small CL and enough lift. Okay. And here I compared 4, 5, 6 series, and additionally I introduced the supercritical airfoil. So have you heard this term, supercritical airfoil? Are you there in the line?
Yes, sir.
Okay, so okay, I'll tell. Before explaining the supercritical airfoil, let me explain the critical Mach number. I think I'm teaching a lot of concepts today itself. Okay. So you know the purpose of airfoil, it is to accelerate the flow. Assume in the front we have the free stream Mach number 0.6, okay, and the flow will get accelerated over the airfoil. Assume this 0.6 is accelerated to Mach number 0.8 on the aircraft, okay. So here also subsonic, here also subsonic, so there is no issue. Now assume I'm increasing the free stream Mach number to 0.7, and this airfoil accelerate that Mach number to the 0.9 on the upper surface of the airfoil. So here also both are subsonic, so no issues. Now further I'm increasing the Mach number to 0.8. Now see, it is accelerated to Mach number 1 or even more than 1. You know the subsonic Mach number, sonic Mach number, supersonic Mach number, etc. Right?
Yes, sir.
Yes, yes.
Okay. So if the Mach number is less than 1, then it is subsonic. If the Mach number is equal to 1, then it is sonic. If the Mach number is greater than 1, then it is supersonic, right? And in the supersonic flow, always it will be accompanied with the shock waves. Okay. See here, the 0.8 is accelerated to sonic, even supersonic flow. So we are getting a small supersonic region over the airfoil. Some locally we are getting one small region. So once there is a supersonic flow, then there will be a normal shock. Okay, so this white color shows the shock wave, and the shock waves are the compression wave. Compression, you know, compression means the velocity will be decreased, pressure will be increased. Compression wave. So what happened? Behind the wave, we are getting the high pressure. Okay, so here supersonic, better acceleration, and so that we are getting the shock wave, and behind the shock wave the pressure is very high because the shock wave is the compression wave. So here we have the very high pressure, and here we have the free stream pressure, the atmospheric pressure, okay, which is low, and due to this pressure difference there is an additional drag that is called wave drag. Okay, already we have one drag that is due to the stagnation pressure and this wake region, right? That is pressure drag, that will be present in all the airfoils. Addition to the pressure drag, we are getting additional wave drag because of this shock wave. Okay, so this is not favorable to the aircraft condition. So we have to avoid this shock wave formation over the subsonic airfoils. Is that clear? If the Mach number increases,
Yes,
1
sir.
point, okay, there will be a sonic or supersonic region, and there will be a shock wave, and there will be additional wave drag, and it has to be avoided. Okay, and so whenever the flow reaches the sonic or supersonic flow over the airfoil, then the corresponding free stream Mach number is called critical Mach number. Okay, so these Mach numbers we will simply call as the local Mach number. Okay, free stream Mach number, or sometimes we'll see local Mach number. But critical Mach number means whenever the flow reaches sonic over the airfoil, then the corresponding Mach number is 0.8. So here, assume this is the 5 series airfoil. Okay, 6 series airfoil. Okay, so 6 series airfoils at 0.8, we got the shock wave. So this is not favorable to the aircraft condition. Then this airfoil should not fly at this 0.8. So if you are using this airfoil in some aircraft, then that aircraft should fly only less than 0.8, maybe 0.75 or 0.7 only it has to fly. It should not go to this 0.8. So this supercritical airfoil defines the maximum speed of the aircraft. Okay, so if you're using 6 series and the critical Mach number is 0.8, then this aircraft should fly with a Mach number of less than 0.8, maybe 0.75 or 0.7. This is the general condition. Now we will see the supercritical airfoil. Up to that clear, right? Critical Mach number.
Yes, sir.
Yes, sir.
Okay. So now instead of this curved airfoil, so they updated the profile further. They are using the flat upper surface. Okay. Now assume we have the Mach number 0.8. Because of the flat surface, it may be accelerated to 0.9 or maybe 0.95 something. Okay. Sorry. Okay, assume it is accelerated to 0.9. So this is the some supercritical NASA supercritical airfoil. So if you use 6 series, the aircraft cannot fly at 0.8. But if you use this supercritical airfoil, because of the flat surface, there is a less acceleration. So 0.8 is simply accelerated to 0.9. If you further increase 0.85, it may be accelerated to 0.95. Okay. And if I further increase maybe 0.9, it may be accelerated to Mach number 1 or 1.1 something. So instead of the 6 series airfoil, if you use this supercritical airfoil, the aircraft can fly up to 0.85. But if you use this 6 series, it may fly only up to 0.75. Okay, that's why in all the commercial aircraft, if we are using this supercritical airfoils, this 6 series, 4 series, 5 series and all, it is used only for the smaller and medium range transport aircraft. Okay, so mostly this 4 series, if you take, the maximum cruising speed will be Mach number 0.5. This also more or less same 5 series, and this 6 series, it may be up to 0.6 or 0.65 Mach number, and this supercritical, it may reach 0.8 or 0.85. Okay, 0.7 to 0.8, within the range it can work. Okay, so all the commercial aircraft, they will use the supercritical airfoil, but they don't use the NASA supercritical airfoil. This is the NASA supercritical airfoil. Now they used to design their own airfoils. If you take Airbus, they will have their own Airbus airfoils. If you take Boeing, they have their own Boeing airfoils. Okay, but it will be similar to the supercritical airfoil. Then only they can achieve the maximum speed. Is that clear? Supercritical airfoil.
Yes, sir. Sir, sir, will this supercritical airfoil will have any disadvantage at lower speeds?
Yeah. A lower speed, it will produce less acceleration, but
Okay,
drag will be less. CL also will be a little bit less. But lower speed, it will be there only during the takeoff and climb, right? Once it reaches that cruising stage,
Yes,
it will be its maximum speed. So all that drawback will be only in this phase.
climb and descent.
Yeah, only takeoff and climb. And here,
So
it will reach its maximum speed. So using
Yes,
the
sir.
supercritical airfoil will be efficient. This 80% only maximum we will take care.
Okay, sir.
Okay. Okay. So now you understand what is critical Mach number and supercritical airfoil, right?
Yes, sir.
Okay. First time I'm taking class to you, so I think many students are simply silent. So whenever you have doubts, you can stop me. I can repeat 10 times also, no issues. Simply sit and go means there is no use. Okay. I don't think okay students are asking again and again. It will be repeating. I don't think like that. If you ask, I will also be interesting. So whenever you have doubt, you can stop me and ask. And okay. After that, here I simply shown the three maximum that is important axis of the aircraft. So this is the longitudinal axis which passes through the fuselage, and this is the lateral axis which passes through the wing, and the vertical one is the vertical axis or directional axis. Okay, so longitudinal axis, lateral axis, vertical axis. Sometime in the definition of angle of attack or some other definitions, they will use angle between chord line and the longitudinal axis, like that they will mention. So that time you should know which is the longitudinal axis, lateral axis. Okay. And here I explain the finite wing and infinite wing. So finite wing is nothing but wing with a wing tip with the end. Okay, so one side is attached, another side there is a end, right? There is a wing tip. This type of wing is called finite wing. Okay, and here if you see the flow over that, there will be a flow over the airfoil, there will be a flow below that airfoil, and there will be a flow in the sides also. So it is 3D. Okay, if you take the finite wing, and infinite wing means the both edges are extended to the infinity distance. And here if you see the flow pattern, it will be only on the upper and lower surface. So this is represent the 2D flow. Is it clear? So finite wing means wing with the wing tip. Infinite means the tip. Both tips are extended to infinity. Wing without wing tip. So this represents the 3D flow. This represents the 2D flow. For example, if you are testing one wing in the wind tunnel, so this is the test section of the wind tunnel. See, they are taking only the one half of the aircraft model. Okay, so this is the root section, and this is the tip section of the wing. And see, there is a space between this wing tip and the wind tunnel. So here there will be a flow on the upper surface, lower surface, and the sides also. Okay, so this is the 3D flow, finite wing. And here you see the wing is attached on the wall. Okay, and here there is a flow only from upper and lower surface. This is the 2D flow. You may ask, what is the advantage of this 2D flow? So whenever if you want to test the airfoil properties, then in the wind tunnel you have to fit the model like that. Both end has to be attached so that the flow will be 2D. Then this will be equal to the flow over the airfoil. Is that clear? So if you want to find the flow over the wing model, you have to take this finite wing model. And if you want to find the flow over the airfoil, you have to take this infinite wing model. That is, both ends are attached on the wall so that the flow is 2D. Is that clear?
Yes, sir.
Yes.
Okay. How much time left? 9:50. Okay. Next, we can see the wing geometries. So, can you tell a few wing geometries which you remember?
Rectangular, tapered.
And that is the picture. Any dimensions? If you want to mark the dimensions for this wing, what are the major dimensions you will note?
A root chord, tip chord.
Okay, so this is the root, this is the tip. Okay, okay, chord.
Taper
okay.
angle.
Okay, taper angle. Chord means distance between leading edge to trailing edge. Okay, next.
Taper ratio.
Span.
Okay. Yeah, the basic one is span, right? The length of the wing, span.
Yes, sir.
Then chord, then only this taper ratio, aspect ratio, everything comes. Okay. Okay, that we will see one by one now. So this is the wing chord. This already we discussed. Distance between the leading edge and trailing edge. If you measure at the tip, it will be tip chord. If you measure this at the root section, then this will be root chord. And we can find the mean chord also. The mean chord approximately somewhere here. Okay, you may ask, what is the use of this mean chord? If you are finding the area of the wing, for example, if the wing is a rectangular shape, okay, so this is span, this is chord, then the area will be span into chord, directly you will take it. But instead of the rectangle, if it is a tapered wing, here if you want to find the area, then we will take the mean chord. Okay, we won't take the root chord or tip chord. We will take the mean chord value and the span value, so that area will be B into C. Is that clear? That's why we will use that mean chord term. Is that clear? Mean chord.
Yes, sir.
Okay.
Yes, sir.
Then next we have wingspan. So it is measured between the wing tips. Okay, here I mentioned different aircraft. So this blue color is the Boeing 747. It was the largest transport aircraft once. Okay, the wingspan is around 68.4 meter. Then they introduced the A380 Airbus aircraft. Now this is the largest transport aircraft. See, it is approximately 80 meter, and you can see the largest one, this pink color. It is 117 meter strato launcher. This is to launch the space shuttle and other aircrafts. Okay, space shuttle, rockets, etc. and all. We can launch from this aircraft. Okay, this is the biggest one, strato launcher. So wingspan means it is measured between the wingtip to wingtip. Is that clear?
Yes, sir.
Yes, sir.
Okay. Then aspect ratio. So aspect ratio means definition is ratio of span by chord. Okay. We have to write it is a ratio of span by chord. Span we denote by B. Chord means C. So we can mention B by C, or sometime we will mention as B square by S also. That is, yeah. So with this B by C, if you multiply another one B by B, then it will be B square divided by S. Okay. So aspect ratio, it is span by chord, that is B by C, or it can be B squared by S. Okay, B squared by area. Both formulas are applicable for aspect ratio. And what is the importance of the aspect ratio? Why it is important?
Sir, if aspect ratio increases, drag reduces.
Okay. Okay, good. So here I mentioned two different aircraft with a different aspect ratio. This is with a lower aspect ratio, so it is short and thick. Okay, this is with a high aspect ratio, so it is long and thin. Okay, and you know the wingtip vortices, right?
Yes.
Okay, I will explain. So this is the wingtip vortices. Okay, from the wing, these vortices will created. So this is the wing model. So we have the free stream flow in this direction. Okay, assume this model is at an angle of attack. So in the upper surface we have low pressure, bottom surface we have high pressure, and this is the free stream flow direction. And in the wing tip, if you see, due to the pressure difference, there will be a leakage flow in the sideways from high pressure to low pressure. Okay, is this clear? This leakage flow. So airfoil is at an angle of attack, and this is the flow pattern. So here we have low pressure, here we have high pressure. Due to the pressure difference, there is a side leakage flow around the wing tip. Because this is high pressure, this is low pressure. There is a flow from high pressure to low pressure. Now what happened? This free stream flow pushes this side leakage flow rearward, so that it curled up and forms the wingtip vortices. Here you can see it has to be like this, the side leakage flow, but because of the free stream, it is pushed rearward and formed as the wingtip vortices. Here also you can see there is a side leakage flow. From the bottom surface, there is a flow coming on the upper surface, but this flow pushes it rearward, so this forms as the wingtip vortices. Is that clear how it forms?
Yes, sir.
Okay. And this wingtip vortices additionally increases the drag, that is called induced drag. Okay. So this wingtip vortices causes additional drag, that is called induced drag. And okay, this is separate. Okay, wingtip vortices and induced drag. Now we will come to the aspect ratio. So if you have the low aspect ratio wing, you see this much portion is affected by this wingtip vortices, and only this much portion is effective to produce the lift. Okay, only this portion is effectively producing the lift. But if you increase the aspect ratio, see only this small portion is affected by this wingtip vortices, and this complete portion is effective to produce the lift. Okay, you can compare this area, how small it is. Okay, only this much. So in the high aspect ratio, only this much is affected, but in the low aspect ratio, this complete area is affected. Okay, so to reduce the wingtip vortices and reduce the induced drag, we are going for the high aspect ratio wings. We don't go for this low aspect ratio wing. And this you can take it as a maximum aspect ratio wing. This is a sail planes. Only the sail plane will have the maximum aspect ratio, maybe 20, 30, etc. and all. In the commercial aircraft, if you see, it will be a little bit less only, because we cannot simply increase the length. If you increase it, then there may be a structural issues. Okay, structural rigidity also we have to take care. We cannot simply increase, so it will break. So if you take the values for the gliders and sail planes, it is maximum 20 to 35, and all other transport aircraft, it will be averagely 10. Okay, the average aspect ratio for the transport aircraft is 10. And if you go for the supersonic, then it will be very less. It is 3 to 5. In hypersonic, it is further reduced to 1. Because at that high speed, if you go for that high aspect ratio wing, it will easily break. So at the high speed, we should have the very low aspect ratio wing, because the velocity is very high. So the small area is sufficient to produce the enough lift. So supersonic, hypersonic, we have the low aspect ratio wing, and subsonic aircraft, they have the high aspect ratio wings. Is it clear? Aspect ratio?
Yes, sir.
Okay. Actually, this wingtip vortices, this is the one way of reducing the wingtip vortices. We have another one forms also that we will discuss in the further slides. Okay, then this is the taper ratio. So taper ratio means we used to denote this by lambda. So this is a ratio of tip chord by root chord. Okay. Tip chord by root chord. And mostly for the commercial aircraft, it will vary from 0.5 to 1. Okay, the taper ratio. And for the supersonic speed, it will be less. It may be from 0 to 0.2. You can see the taper angle. Okay, there may be a small chord length here. It may be 0.1 or 0.2. Here it may be 1. Then the ratio will be maybe 0.1. So for the supersonic, we are going for this more tapered wing. I will explain why we are going for this more tapered wing. But for the commercial transport aircraft and all, it will be in the range of 0.5 to 1. And this is just a rare design. Here they went for the taper ratio of 2. So here we have less chord, here we have more chord. But practically we don't go for this type of model, because this will produce more lift, then the more bending stress, etc. will be there. So mostly we won't go for this more than 1 for the taper ratio. Is that clear? Taper ratio definition, tip chord by root chord. And what is the use of this taper ratio? I'll explain here. So this is the elliptical wing shape. Okay. And experimentally and theoretically they found this produces very minimum wingtip vortices and very minimum induced drag. Okay, we cannot say that the induced drag is 0. It produces the minimum wingtip vortices and the minimum induced drag. Okay, but manufacturing this elliptical shape is very difficult. So instead of this elliptical shape, we are going for the tapered wings. For the purpose only, we are using the taper. Is that clear? Hello?
Yes, sir.
Okay. So
Yes, sir.
actually, in the theory also, we will prove this elliptical planform produces the minimum induced drag. Okay. So the manufacturing, everything is very complex. So instead of elliptical wing shape, we are going for the tapered wing, so that it will produce the minimum induced drag. In the supersonic case, I'll explain that further. Okay, because this we will call it as sweep. Why there is this much sweep and all, I will explain that. Okay, here. So next one is the sweep angle. So sweep angle, mostly we are measuring between this axis. What is this axis? Just now I explained, right? I explained the 3 axes: longitudinal, lateral, and vertical axis. Yeah, this is the lateral axis. Okay. So it is measured between lateral axis and this quarter chord line of the wing. What do you understand from this quarter chord line? This is the leading edge line, this is the trailing edge line. So here we may have the root airfoil. Here we may have the tip airfoil. And they are taking 25% from the leading edge in the root section. Similarly, here also 25% from the root section. Then that 2 point they are joining, that line is called quarter chord line. Okay. Or if you are drawing the line at the 50%, then that will be the C/2, maybe half line. There is no name like that. Okay. So here they have taken 25%, so they are calling that as quarter chord line. Okay. So sweep angle means it is measured between the lateral axis and the quarter chord line. Is that clear? The definition, it is measured between the lateral axis and the quarter chord line. So here I compared straight tapered wing and swept back tapered wing. You can see the difference. Okay. So this is the quarter chord line. Here it is straight. Even though the wing is a tapered, this quarter chord line is a straight. And here also it is tapered. You can see the chord, it is varies. Here it is very high, here it is very less. So this is a tapered wing, but the quarter chord line is deflected rearward for this sweep angle. Now do you understand the sweep angle, right? You should not compare this with the sweep angle. Okay, this is not the sweep angle. So this line only you have to check it. Even though it is angle, it is due to the taper. Okay. So angle between lateral and this chord line only you have to take it. That is quarter chord line only you have to take it. Is that clear? Sweep angle. So this is straight tapered wing. This is the swept back tapered wing. Angle between lateral axis and quarter chord line. Is that clear?
Yes, sir.
Okay.
Yes, sir.
And what is the purpose of that sweep angle? That I will explain here. So just now I explained about the critical Mach number, right? Assume this is the wing and this is the airfoil, maybe 6 series airfoil, for example. If you keep this wing in the Mach number of 0.8, this 0.8 will be accelerated to Mach number 1 or 1.1. Then there will be a shock wave. Then there will be additional wave drag. Okay. So this rectangular wing cannot go in this Mach number 0.8. Instead, if I rotate this wing with some certain sweep angle, then the wing model will be like this. Now this is my airfoil profile. Okay, because I deflected the wing rearward. This is my airfoil. Assume this wing also I am keeping in the same Mach number 0.8. Now see, this flow now have two components. Okay, we have to see flow over this airfoil only. That means this reference line only we have to take it. Okay, now if you check the Mach number in front, assume the sweep angle is 30 degree. Okay, so this is 0.8 and this is 0.8 into cos 30. That will be approximately 0.7. Okay, because of 30 degree, now flow over the airfoil. If you take here it is 0.7, that 0.7 may be accelerated to 0.9. So if you give the sweep angle using the same airfoil, we can fly up to 0.8. Is it clear?
Yes, sir.
Okay. So now this is the airfoil line. Even though it is 0.8 here, because of this inclination, the 30 degree, now in front we have 0.8 into cos 30 degree, that means 0.7. The 0.7 may be accelerated to 0.9. So this can go for the 0.8. So the sweep angle is to increase the critical Mach number. So in this thing, the critical Mach number may be 0.9. At 0.9, we may get the shock wave, etc. and all. Okay, so to increase the critical Mach number, we will use the sweep angle. So instead of 30 degree, if we use 45 degree, so the 0.8 is converted into 0.6. Okay, the 0.8 may be converted into 0.6 in front. That 0.6 may be accelerated to 0.8 if you increase the sweep angle. The same thing is shown. Because of 45 degree, 0.8 is converted into 0.6. Because of 30 degree, 0.8 is converted into 0.7. So the purpose of the sweep angle is to increase the critical Mach number. And this is swept back wing, and this is the swept forward wing. Okay, but mostly in the commercial aircraft, we will use the swept back only. We won't go for the swept forward, because if you use this swept forward, here there will be a more stresses acting in this point, and there will be a flutter issues also near the tips. So the tip may easily damage. So for the safety purpose, we are going for the swept back wings. Is that clear? Very rarely you can see this swept forward wings. All the commercial aircraft, everywhere we are using only swept back wing. So using that sweep angle, we are increasing the speed of the aircraft. So it can fly at more speeds. We can increase the critical Mach number. Here they mentioned the sweep angle range. You see all the commercial aircraft, it will be approximately 30 degree. Okay. And if you go for the fighter aircraft, it will be further increased to 40, 50. And if it is supersonic, it will be further increased. That's why in the fighter jet aircraft and all, we have the more sweep wings. Okay, it is of 75, 60, etc. and all. So transport, the sweep angle range is approximately 30, and in the smaller aircraft, if you take, it will be less than 30. Even if you take a single-seater aircraft and all, it will be simply straight wing. Okay, there will be sweep angle and all, because the Mach number will be simply 0.5. Even at maximum, it may oscillate to 0.6 or 6.5. Okay, it won't go to sonic, supersonic, etc. and all. So there is no need of sweep. Because if you give sweep, then there will be a loss of lift. If you compare the lift produced by the rectangular wing and the swept back wing, this will produce more lift. Okay. So for the smaller aircraft, as the cruising speed is less, we are going for the only taper or rectangular wing. We don't go for the sweep wings. Is that clear?
Yes, sir. Yes, sir.
Yes.
Okay. Okay. Can we proceed or we can stop? I'm asking you only. Shall I proceed further? Okay. The next one is dihedral and anhedral wing. So this is the lateral axis. With reference to the lateral axis, we are tilting the wing above or below. Okay. If you tilt the wing above, then this is dihedral, and if you tilt the wing below, then this is anhedral. And which type of wing have you seen mostly in that commercial aircraft? Dihedral or anhedral type?
Anhedral.
Dihedral. So in all the commercial aircraft, mostly we'll use the dihedral wing because this is more stable configuration. Okay, this is stable. Actually, this is unstable. So this anhedral, mostly we will see it in the fighter jets, where we need the better maneuverability. Okay, I will explain how it is stable, how it is not unstable, etc. So this is the dihedral wing. Okay, initially it is in the steady level condition. So both wings produces equal amount of lift. Okay, and if you want to find the reference area, then from the top you have to see. So this is your reference area. That means this length will be equal to this blue color line. Okay, this is the reference area. This only creates the lift. Okay, even though here the length is more, this we should not take. Okay, so for the lift, we have to take the top view of the wing. So this is our reference area. This is the affected wing area to produce the lift. Okay, this is one case. Now assume this aircraft is side slipping. Okay, so due to the side slip, this wing is coming to the horizontal direction. Now if you see the reference area, this time you have to take that yellow color line. Okay, you know, so compared to this blue color line, this yellow color line is more right. This is a right angle triangle. Okay, so this line length is more, then this area is more, then this wing produces more lift compared to this. So now what will happen? Initially, there is a side slip of the aircraft that makes the more reference area on this side, so lift also more. So it creates the balancing moment, so that even if you side slip, the aircraft will be automatically balanced and come to its original position. So this type of stability we can get it if you go for the dihedral wing. That's why in all the commercial aircraft we are going for this dihedral wing. Is that clear?
Yes, sir.
Okay.
Yes, sir.
I used to explain with this with a notebook in the classroom. I feel that is very good. Okay, you got it right. So the wing length is in the car, span is increasing, area also increasing, so the lift also increasing. So there is a balancing moment, so that the aircraft is coming to its original position. So for this type of stability, we are using dihedral wing to the commercial aircraft. And now come to the anhedral wing. Now this is the anhedral wing, steady level flight. So both wing produces the same amount of lift. Now assume there is a side slip, okay, to the right hand side. Initially, so this is the reference area. Okay. This is the reference area that created the lift. Okay, that is this length. But now, because of the side slip, now this is the reference area which produces the lift. So compared to this length is more. So here area is more, lift also more. So here what happens? Already the aircraft is side slipping to the right. Now this also produces additional moment. So the aircraft will easily roll. Okay. So this type of rolling maneuverability and all, it is needed only in the fighter aircraft. So we are going for this anhedral type of wing in the fighter aircrafts, not in the commercial aircraft. The commercial aircraft, if you use, then it will be very difficult to stabilize the aircraft, then it may fail. Okay, so dihedral is stable configuration we are using for commercial aircraft. Anhedral is very unstable, so it is good for the maneuverability. So we are using it in the jet aircraft. Is that clear? Anhedral, dihedral.
Yes, sir.
Yes, sir.
Okay, you can see in the fighter jet we are using the anhedral type of wing, and in the commercial aircraft we are using the dihedral, and nowadays we are using variable dihedral. This is not the straight line. Okay, this is a variable dihedral which is inspired by the birds. Okay, and all the commercial bigger aircraft, transport aircraft, we are using the variable dihedral. And here you can see this also dihedral. This is the cargo aircraft. So mostly this anhedral we will use it for the fighter, and we will use it for the high wing configuration. So these things are low wing configuration, right? You can see this is the fuselage, below that we attach the wing. But here, this is the fuselage, above that we attach the wing. So this is the high wing configuration. Okay, and high wing configurations are very stable configurations. Okay, it is very difficult to do the maneuvers in the high wing configurations. But if it is the cargo aircraft, then the weight will be more. Then we have to add more engines. So we have to give some clearance. Okay, so mostly we will go for the very big large aircraft. It will be of high wing, but it will be very stable configuration. So it will be very difficult to do the little maneuvers and all. In that case, to introduce that maneuverability, they are having the anhedral type, anhedral wing. Is that clear?
Yes, sir.
Okay. So only in the fighter and that high wing configuration, we are going for anhedral. Other commercial applications, we are going for the dihedral.
So, but why is it so that in high wing configuration there would be like it would be much more stable as compared to mid or low wing?
So here they explain. So this is the flow pattern they observed in the high wing and low wing configuration. So in the high wing configurations, okay, if you turn like this, okay, assume there is a side slipping to the right hand side. Now this is the wind direction. This hits here, and there is a more pressure in this region. Here low pressure, here high pressure. So there is a force in this direction that push back this configuration aircraft to the original position. Okay, again it will be in the stable configuration. Even here they explain the flow patterns and all. what they observed experimentally. So this is high wing, right? So in the high wing, okay, here they explain the side slip in the left hand side. So here there is a more flow, so this produces more lift, but here due to the fuselage, the flow is going downwards, so that reduces the lift. So this side more lift, this side less lift. So there is a rolling moment, balancing moment, so it is come back to its original position. Even if you try to side slip in the left side, because of this differential lift, there is a balancing moment, again it goes to the original position. So side slipping is very difficult. But if you go for the low wing configuration, here they found, so it is side slipping in this direction, but this produces less lift here, more lift here. So this is produces additional moment in the same direction. So it will easily side slip in this direction. Okay, so compared to this is very stable. Okay, so both are side slipping in the same direction, but because of the flow direction, here produces high lift, but this produces high lift in this direction. So this is a balancing moment, but this is further accelerating the side slip. Okay, so compared to this low wing, the high wing is very stable. So even if you try to side slip, this configuration it is easy, but here it is very difficult because there will be an automatic balancing moment. So in that configuration, they are going for the anhedral. And in this configuration, they are going for the dihedral. So that even if you side slip, this will produce little bit balancing moment, so that we can stabilize the aircraft. We can control the aircraft. Is that clear?
Yes, sir.
Okay. So you can see almost in all the high wing, there will be a dihedral. In all the low wing, there will be a sorry. So the angle above means positive, below means negative. Okay. So this is dihedral. This is anhedral. So this is negative. This is positive. In all the low wing, there will be a positive value. In all the high wing, there will be negative values almost. Okay. Okay, once again, mission profile that is already explained. Then wing setting angle. So we can call this as wing setting angle or incident angle. Actually, angle of attack is different, and this wing setting angle is different. Okay, don't compare, confuse with this incident or angle of attack. It is totally different. So wing setting angle means while manufacturing the aircraft itself, they will keep the wing at a certain angle. Okay, so they won't fit the wing at 0 degree angle of attack. While manufacturing it itself, it will be fitted at some few angle. Mostly it will be from 3 to 5 degree. Okay, so this is measured between the chord line of the wing and the longitudinal axis. Okay, so the wing setting angle is measured between chord line and the longitudinal axis. While manufacturing itself, the wing is attached with some at a certain angle. The reason is, in this cruising stage, aircraft will be in the steady level condition, and if you are attaching the wing in the 0 degree angle of attack, then it will not produce enough lift. Okay, so for that reason, while manufacturing itself, they are giving some small angle which varies from 3 to 6 degree, so that even though the aircraft is at the steady level condition, they are having some small angle which is sufficient to produce the CL and lift. Is that clear? Wing setting angle. Hello.
Yes, sir.
Yes.
Are you there?
Yes, sir.
Okay. 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 So it won't be at 0 degree. It will be at some small angle while fitting the wing in the aircraft. That is wing setting angle. So here you can see the range. Okay, 0 to 6 degree, and in all the transport aircraft, it will be in the range of 2, 3, 5, etc. Only in the jet aircraft you can see the 0 degree, because there the velocity is very high. So even 0 degree with a cambered airfoil will produce enough lift. Okay, in all other commercial aircraft, the range is from approximately 3 to 6. Okay, then wing twist. Actually, this is the straight wing. Okay, this is the twisted wing. You can see the different side. What do you mean the twisting of the wing? So this is the example. The hummingbird, you can see the twisting of the wing. So the same type of wing twist is applied to our aircraft wing also. So we have two types of wing twist. One is geometric twist, another one is aerodynamic twist. So if you are changing the root section and tip section airfoil angle of attack or incident angle, that is called geometrical twist. Okay. So compared to the root section airfoil, the tip section may have lower angle or higher angle. If you twist like that, that is geometrical twist. And aerodynamic twist means by changing the airfoil profile, we can introduce small twist in the aircraft. That is called aerodynamic twisting. Okay, by changing the airfoil profile from root to tip, we can introduce a small twist, that is called aerodynamic twisting. And by changing the incident angle, we can produce a twist, that is a geometrical twist. And if the tip airfoil has the less angle compared to the root section, that is called washout. Okay, so less angle means this may be at 5 degree, this tip section may have the 2 degree, or even it may have some negative angle of attack, negative incident angle. Okay, like that. If you reduce the tip section airfoil incident angle, then this is called washout. And if the tip section has more angle, for example, root section 0 degree, tip section 5 degree, okay, like that, tip section has more angle, means this is washing. Okay, this is the definition. Geometrical twist, aerodynamic twist. In the geometrical twist itself, there is a washout and wash-in. Washout means tip will have low angle, wash-in means tip will have more angle.